Block A of mass 2.0 kilograms and Block B of mass 8.0 kilograms are connected as shown above by a spring of spring constant 80 newtons per meter and negligible mass. The system is being pulled to the right across a horizontal frictionless surface by a horizontal force of 4.0 newtons as shown above, with both blocks experiencing equal constant acceleration. Part A. Calculate the force that the spring exerts on the 2 kilogram block. So in order to do this, we first want to kind of figure out the acceleration of the system, because both blocks are going to accelerate together. If we find the acceleration of the system, we'll find the acceleration of each block. And the only force acting on block A, moving it to the right, is the spring force. So in order to calculate that force, we're just going to multiply mass times acceleration of block A to get that answer. But first we need to figure out what the acceleration of block A is, or the acceleration of the system. So to do that, we're going to first write out the Newton's second law equation that says the sum of all forces externally to the system is equal to the total mass of the system times the acceleration. And the total mass of the system is just going to be ma plus mb. And then rearranging for A, we see that the applied force being 4 and the total mass being 10, we get an acceleration to the right, so positive 0.4 meters per second squared. And then block A is being accelerated by this spring force, so mass times acceleration will give us the force of the spring on block A. Plugging in the values, we get that force is 0.8 newtons. Part B. Calculate the extension of the spring. Well, let's start by drawing a free body diagram. So, like we've mentioned in Part A, the force of the spring to the right is responsible for moving the 2 kilogram block. So, setting up Newton's second law, we can calculate that force, again, is 0.8, and that the force of the spring is also going to be equal to the spring constant times the distance that it's stretched, delta x. So if we plug in first let's rearrange for delta x, which would be the force of the spring divided by the spring constant, and plugging in our values, we get 0.01 meters, which is also 1 centimeter. Part C is the magnitude of the acceleration. First we have to read a new situation. Okay, so the system is now pulled to the left, as shown below, with both blocks again experiencing equal constant acceleration. Part C is the magnitude of the acceleration greater than, less than, or the same as before. Well, the way we calculated acceleration was the external force divided by the total mass. And because the external force is still 4 and the total mass hasn't changed, really the acceleration is also going to be the same. So we can say that it will be the same because acceleration is external force divided by the mass, and because neither of those two variables changed, we will have the same acceleration. Technically, we could say that the acceleration is negative, but of the same magnitude, but they're really looking for the magnitude, so the magnitude is going to be the same. Part D is the amount that the spring is stretched greater than, less than, or the same as before. Well, let's draw we don't really need to draw a free body diagram. We could, but the spring force is now going to be acting on block B. So figuring out what that force is, we can multiply the mass of B, which is 8, times the acceleration, which is still 0.4, to get a new spring force of 3.2 newtons. And using the Hooke's law equation, we can say that displacement is the force of the spring divided by the spring constant, and since our force of the spring is now 3.2, we're going to get a larger stretched distance. So 0.4 this time instead of 0.01. So that is greater. For part E, in a new situation, the blocks and spring are moving together at a constant speed of 0.50 meters per second to the left. Block A then hits and sticks to a wall. calculate the maximum compression of the spring. Well, when block A hits the wall, B is initially moving with kinetic energy, and that's all the form of energy that B has. And then when it hits the wall, it's going to lose all of that kinetic energy, but it's going to be transferred by compression of the spring into spring potential energy. So in order to solve this question, we really want to set up a conservation of total mechanical energy for our system. And like I just said, it's going to start out having kinetic energy, so 1/2 mass B times velocity squared is going to equal the compression energy that goes into the spring when it comes to a stop, 1/2 k delta x squared. And we're trying to solve for the compression distance delta x, so we just want to divide by k on both sides and then take the square root. Whoops, and I missed the square root here. So plugging in our values, we get a compression distance of 0.16 meters.